All right, what is an interaction and why do these forces come in pairs? So an interaction is when two objects act on each other with a mutual force. What I mean by that is like you push a cart and the cart pushes against you. Gravity pulls you down from the earth and you pull on the earth with gravity. Like any of these interactions between two objects when they come in, doesn't necessarily have to be physical contact, they just have to act on one another. So two objects that act on each other with a mutual force. Why do they always come in pairs? Because both objects are required for the force to exist. For example, if I punch the air, what's my force? I don't know, because I didn't actually apply it to anything. So like, I pushed really hard, I could calculate the velocity, but I can't calculate the force because in order to calculate the force, I have to have something, I have to have force on something. Okay? Now if I punch Mike Tyson in the face, then I can calculate the amount of force I punched him in the face with. Okay? But I can't calculate a force if I don't do anything. Okay? I can apply the force that my muscles apply, but I can't apply the force that my hand would apply because it doesn't hit anything. You have to hit something or interact in order to find a force. Yeah.
So, like, if you're running, is running with weights, is that going to like eventually make you faster than just running in general?
There is a reason why people do that, or like you've seen like people run with like a parachute behind them. Because you have to apply a force to move your body and against air resistance or against like the weight pushing down on you more. And so that does increase the strength that you would.
So the more force you output.
Mm-hmm. Right, because you apply more force because there's more force acting on you. Yep, you're exactly right. Okay? So that's what an interaction is. Okay. Newton's third law. Is the same than what we've done with net force. No. This is not what we've done with net force. Net force is the total force acting on one object. Total force acting on an object. Okay? Interactions are two objects acting against each other. So an interaction acts on two objects. A acts on B and B acts on A. So interactions are always the same and on two different objects. With net force, the forces don't have to be the same, right? We talked in that front page on this practice. We've got a force up of 40 and a force down of 25. They aren't equal enough. They aren't interactions. They're acting on the same object, and they're not the exact same thing. Okay? One is air resistance, and one is gravity. Okay? These are the same force, and they're on two different objects. So this is not Newton's second law. It's different than that. So what is Newton's third law? Newton's third law is every action has an equal and opposite reaction. And here's how I think of it. I think of it like this. A acts on B, which equals B acts on A. Okay, let me tell you a ridiculous way to remember this. This is ridiculous. This is something my children do. I don't really know why or how they started it. I am not intending this to be offensive to anyone. I don't think it will be, but just know this is just a silly thing my kids do. My kids play this game where they talk to each other like they think Russians talk. Okay? So they do this. They say, in Soviet Russia. Okay? This is how they start. They say, in Soviet Russia, and they do it like this. In Soviet Russia, you no eat ice cream eat you. Okay? This is what they do. I don't know why, they just think it's funny. Okay? But it always, here's how the joke works. It's, in Soviet Russia, you don't do this does that to you. That's how this works. A acts on B, and B acts on A. So, in Soviet Russia, you no drive car drive you, right? In Soviet Russia, you act on car, and car acts on you. It's ridiculous. I don't know why my children do it, but it helps understand this idea of whatever A does to B, B does to A. So let's look at this, okay? The action-reaction force. So what is the reaction to your hand punching the wall? So, your hand punch wall, wall punch your hand, okay? So the reaction force to your hand punching the wall is the wall punches your hand. Yeah. So, here's my example of this, right? So, here's the wall. Here's my hand. I apply a force into the wall. So there's a force from my punch. The wall will apply a force into my hand. That will be the exact same, but in the opposite direction. And you all know this, because if you punch hard, it hurts more than if you punch soft. Because if you punch soft, you apply less force to the wall, so the wall applies less force to you. Okay? It is always equal, it is always opposite. If you punch the wall hard, it will never punch you back soft. Okay? If you punch the wall soft, it will never punch you back hard. But it will always punch you back, no matter what. Okay? And that's because of how these action-reactions work. What? Look at number 19. Okay, number 18. If the force between us and the earth and us are equal and opposite, why don't we see the earth move when we fall? Okay, here we go. I'm going to jump off the desk. What? Because I'm going to make the earth move. Hold on one second. I got to jump off the desk. There's someone out there. Okay? So, I'm going to apply, the earth is going to apply a force to me. So I'm going to make the earth move because I'm going to apply a force to the earth. So hold on, the earth's going to move, so just prepare yourself mentally, okay? Here we go. 3, 2, 1. You didn't fall out. Good job. Good job. Thanks for waiting. The earth did not, I thought you were going to do. So right at the end. Okay? So, why didn't we see the earth move? No, I do apply force to the earth. It does, well, it applies a force to me, that's why I fall. The earth jumped on me. Yeah, that is the reaction. I jump down because of the earth, so the earth jumps up because of me. Yeah. So why not? Because the force acting on me is big enough to make me move a lot. But the force acting on the earth is not big enough to make the earth move a lot. Okay? So the forces are equal and opposite, but the reactions to those forces are not equal and opposite. So the force between me and the earth, so the force is equal and opposite. But the results isn't. Let me show you. F equals ma. Okay? So we use, here we go, A equals F net over m. If I multiply the mass over, I get this, F equals ma. So here's the force from the earth on me. Here's the force from me on the earth. They are equal and opposite. Those forces equal mass times acceleration. What's the difference? I weigh less and the earth weighs more. If those forces are going to be the same, then what has to be true of the acceleration? My acceleration has to be more and Earth's acceleration has to be less. Okay, I'm going to do this for you really quick here, okay, just to show you. So we already know what the acceleration on me is. What's the acceleration on me? 9.8. The acceleration on me is 9.8. The force acting between me and the Earth is, I weigh 185 pounds, so in newtons that is about 800 newtons. Okay? About 800 newtons. So all I have to do to find the acceleration of the Earth is divide by the Earth's mass, which I know you guys all know is 1.99 times 10 to the 24th power. So 800 divided by 1.99 times 10 to the 24th power that is the acceleration I put on the Earth. 4.02 times 10 to the negative 27 meters per second squared. In other words, it is 0.00000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000 that is the reason why you don't notice this all the time. You don't notice it all the time because sometimes the result of the force is very different. But the force is not. The force is exactly the same, but the result doesn't have to be. Okay, so let's look at the paper one. If I punch a wall as hard as I can and a sheet of paper as hard as I can, okay, the wall is going to hurt my hand and probably break it, especially if I'm a major league pitcher and I punch the wall after I have a bad outing, which I feel like happens once a year. But the other doesn't. Here's the thing I want to make you understand. It's an interaction. It's two objects acting on each other. So when I'm figuring out the amount of force, it depends on me and how hard I punch, but it also depends on what I punch. If I punch a pillow, which is soft, I'm going to have an overall smaller force because it doesn't take that much force to hit the pillow. So even if I punch as hard as I can, the actual interaction between my hand and the paper will be small. But the interaction between my hand and the wall will be large. So interactions depend on both objects and the force value is calculated between them. if I could measure, if I had a force meter in a pillow and I have a force meter in a wall, and I punched the force meter on the wall and I punched the force meter on the pillow as hard as I could on both, they would not read the same thing because they're two different interactions. One's an interaction between me and a pillow, one's an interaction between me and the wall. The interaction between you and the paper is small. The interaction between you and the wall is large. It's just like me jumping off the table. The interaction between, like, the force is the same, but if I jumped off of, I don't know, let's say I was floating in space and I jumped off of a spaceship, okay? The interaction between me and the spaceship would be different than the interaction between me and the Earth. Okay? Because the Earth is huge, and the spaceship is not. So the interactions would be different between those. Okay? Any questions on Newton's third law and how those interactions work there?